Hello everyone, this is Adit Sharma.
And myself, Ishani Sharma. So today we'll be presenting on the topic Adversarial Machine Learning in Computer Vision. Deep neural networks have demonstrated phenomenal success, often beyond human capabilities in solving complex problems, whereas recent studies show that they are vulnerable to adversarial attacks in the form of subtle perturbations to inputs that lead the model to predict incorrect outputs. So this presentation will be mainly about the study and literature review of threat of adversarial attacks on deep learning in computer vision. So starting with the introduction, deep learning is provided major breakthroughs by being able used to decipher hard scientific problems like the brain circuit analysis of mutation in DNA, self-driving car surveillance, malware detection, etc. But a very major weakness that has been found is that despite their high accuracies, modern deep neural networks are surprisingly susceptible to adversarial attacks. Like in these images, we can see that the models like CAFENet and GoogleNet, when small perturbations were added to the images, the network predicted wrong labels with high confidence values. Some of the important terminologies with this respect that one must know are like adversarial example or image. So, a modified version of a clean image that is intentionally perturbed, that is by adding noise in order to confuse or fool a machine learning technique, such as deep neural networks. So, such an image is called adversarial image. When the noise which is added to the clean image is an adversarial example. The adversarial training is when adversarial images Adversarial training uses adversarial images besides the clean images to train the machine learning models. And adversary is more commonly used to refer to an agent who creates an adversarial example. However, in some cases, the example itself is also called an adversary. Another important terminology is black box attacks. So, black box attacks feed a targeted model with adversarial examples during testing that are generated without the knowledge of that model. In some instances, like it is assumed that the adversary has a limited knowledge of the model. That is about maybe example its training procedure or its architecture, but definitely does not know anything about the model parameters. Another important terminology that is exactly opposite to black box attack is the white box attack, which assumes the complete knowledge of the targeted model, including its parameter values, architecture, training method, and in some cases, training data as well. Then, fooling ratio rate indicates the percentage of images on which a trained model changes its prediction label after the images are perturbed. A one-shot or one-step method generate an adversarial perturbation by performing a single-step computation. Targeted attacks are the ones which fool a model into falsely predicting a specific label for the adversarial image. And transferability refers to the ability of an adversarial example to remain effective even for the models other than the one which was used to generate it. So, reiterating the important terms, like for example, if I introduce some noise to an image, then I will be the adversary. The noise added will be the adversarial perturbation, and the perturbed image generated will be the adversarial example or the adversarial image. Okay, so moving forward, now we'll review some of the methods that attack deep neural networks, mainly focused towards classification and recognition. The first method we'll be discussing is the box constraint method. So here, let we denote the clean image with IC, which is a vectorized clean image. And the subscript C here denotes that the image is clean. So to compute an additive perturbation, we need a non-trivial solution to this equation. So we get the perturbation by solving this equation for the non-trivial solution. So it is observed that the perturbations computed for one neural network using this technique were also able to fool multiple networks. So here basically the box constraints are introduced on the perturbation to limit the magnitude of changes. For each element of the perturbation vector, these constraints ensure that the perturbation remains small and imperceptible to the human eye. Like again here in the image, it is an illustration of the adversarial uh, examples generated using LXNet. The predicted labels of the adversarial examples are also shown. So the original label is a different one. When some noise is introduced to the original clean image, then it produces an adversarial example with a completely false output but high confidence value. Moving to the next method, this is a very important method, which is the fast gradient sign method, FGSM. So here the objective of an adversarial attack is to find a perturbation which, when added to the original input data, maximizes the loss function L with respect to a target class Y. So, so the robustness of the deep neural networks against the adversarial examples could be improved by adversarial training. So an adversarial perturbation for a given image can be computed by solving this equation, which where this denotes the grade computes the gradient of the cost function, which is to be maximized to a limit such that the perturbation is not perceptible to the human eye. So here the size of the perturbation is controlled by the epsilon parameter, which determines the trade-off between the adversarial example's effectiveness and the perceptibility to the humans, which is the very uh, important factor to this method. So the method for solving this equation is often termed as the fast gradient sign method, and that in the original work, and that is why this method is named like that. For the one-step target class variation of FGSM, which states that instead of using the true label of the image in the equation, the target of the least likely class was predicted by the network for IC. The goal here is to maximize the probability that the network predicts the target L target, which is a specified target label, as the label of the adversarial example. So basically, here we are specifying a particular target that has to be that the model has to. So L target is the label that the model should give as an output. So random class can also be used as the target class for fooling the network. However, it leads to less interesting fooling. For example, misclassification of one breed of dog as the another dog. But it ultimately remains a dog, so that is referred to as less interesting fooling. Moving on to the third method, which is the basic and least likely class iterative methods. So the one-step methods that perturb the images by taking a single large step in the direction that increases the loss of the classifier. That is one-step gradient ascent rather than gradient descent, since it's we are learning adversarial training. So here we are referring to gradient ascent. That is, our main goal is to maximize the gradient to that extent such that the noise introduced is not perceptible to the human eye. So an intuitive extension of this idea is to iteratively take multiple small steps while adjusting the direction after each step. Further, moving to the fourth method, which is the Jacobian based saliency map attack, JSMA. So this algorithm basically modifies the pixels of a clean image one at a time and monitors the effects of the change on the resulting classification. Performing the monitoring, a saliency map is used using the which is performed by using the gradients of the outputs of the network layers. So in the map, a larger value indicates a higher likelihood of fooling the network to predict the target as the label of the modified image instead of the original label. Thus, the algorithm performs targeted fooling. That is, we define a particular target, and we hope that after the perturbation is introduced, the model each time predicts the output to be same as the defined label. So once the map has been computed, the algorithm chooses the pixel that is the most effective to fool the network and alters it. This process is repeated until either the maximum number of allowable pixels are altered. That is, if the this limit is the one which specifies that if we modify more pixels, then the perturbation or the noise which has been introduced will be perceptible to the human eye. So that is not allowed here, because our main goal is to only modify that number of pixels such that the human eye is not able to depict the difference between the clean image and the perturbed image. The next method is the one pixel attack, which is an extreme case for the adversarial attack in which only one pixel in the image is changed to fool the classifier, and that leads to high average confidence of the networks on the wrong labels. So, like here, we can see the examples in the pictures just by modifying one pixel of this image, which was originally of the dog. Like the different models predicted as aeroplane, deer, or horse. So it's just just like here. the original label being dog, but just by modifying one pixel, the model is classifying it as a frog or an automobile. So they randomly modify the elements of the vectors to create children such that the child competes with the parent for fitness in the next iteration. So while the probabilistic predicted label of the network is used as the fitness criterion, the last surviving child is used to alter the pixel in the image. So I'll be demonstrating the code of this method in a while. Then the next method is the deep fool. The deep fool algorithm initializes with the clean image that is assumed to reside in a region confined by the decision boundaries of the classifier. The region then decides the class label of the image. So here again the decision boundaries are defined by the fact that we can introduce only that much noise in the image which the human eye is not able to understand. The last method which I'll be demonstrating is the universal adversarial perturbation. So this is a very important concept. Universal perturbation is able to fool a given model on any image with high probability. So universality refers to the property of a perturbation being image agnostic as opposed to having good transferability. So that means that a model which has been perturbed using the universal adversarial perturbations that works well on any image apart from just working on the one on which was used to train it. Further, an important concept is p-norm of perturbation. So for a perturbation vector del of length L, the LP norm is calculated by using this formula. So different norms can be used depending on the attack strategy that like L1, L2, L infinite or the LP norms with variable values of P. So basically, the choice of this norm affects the characteristics of the adversarial perturbation and how it influences the model's behavior. So researchers basically explore various norms and perturbation strategies in order to understand and defend against the adversarial attacks. Here is a summary of the attributes of diverse attacking methods that we have discussed so far. So here black and white box, as we had discussed in the starting, black box attack refers to the one where the where the attacking algorithm has no knowledge about the model parameters, whereas in the white box attack, the whole of the knowledge about the model parameters architecture is known to the adversary. So, and then the targeted and non-targeted refers in the targeted attacks, we specify a particular class label and we expect the model to classify each and every image uh, to that target label only. Whereas in non-targeted, we are fine with the model classifying the image to any category apart from the correct one. This image specific and universal, as we discussed, universal is the one which will work on any image apart from the one which was used to train it. Then perturbation norm L infinite, L2, L naught, which different researchers use in order to understand the perturbation strategies and defend against the adversarial attacks. Then one shot and iterative learning and the strengths, the more the stars, the more the strength of the model. So universal perturbations, as we can see, are the most powerful amongst the all which we have discussed so far. Now from here on, these are the slides which are basically so attacks beyond classification and recognition. So here are the attacks on the encoders and the generative models. So it has been investigated that adversarial attacks for autoencoders and proposed a technique to distort the input image to make it adversarial that misleads the autoencoder to reconstruct a completely different image. So these adversarial attacks works on autoencoders as well as has been reported. So it is though autoencoders seem to be much more robust to adversarial attacks than the typical classifier networks. Then the adversarial attacks work on the recurrent neural networks too. So these RNNs, which are the deep learning models that are particularly suitable for learning mappings between sequential inputs and outputs. So the adversarial attacks are capable of introducing perturbations to these networks too. Then similarly, the attacks on deep reinforcement learning and the attacks on recurring neural networks. So here in the image, as we can see, by introducing a simple perturbation, the whole neural network can be made to misclassify the images. Then further attacks on the face attributes. There's like although face attribute recognition can also be categorized as a classification problem, we separately review some interesting attacks in this direction, like the facial attributes emerging soft biometrics must be automatically and reliably extracted from images in order to be usable in standalone systems. So here we can see in this image, just by introducing this little noise, that the clean image, which was categorized as wearing lipstick, was uh, transformed to non-wearing lipstick, and similarly here by introducing this noise the gender of the image is changed. Though this is imperceptible to the human eye will not be able to detect this difference. So here the fast flipping attribute method is used. This technique generates more adversarial examples than the traditional algorithms, and the adversarial robustness of the DNNs vary highly between the facial attributes. So these are some of the attacks in the real world, which is the road sign, like the road sign attack. Here the image shows that the success rate of fooling the classifier in all the shown images is 100%. That is, the distance and the angle to the camera does not affect the confidence value. Then the cyberspace attacks, which are the substitute uh, cyberspace attacks, and the robotic vision or the visual QA attacks. These conclude that the adversarial examples pose threats to not only the image classification models but also more complicated VQA models. Okay, so now I'll be demonstrating some codes. So this is here I'll be demonstrating the FCSM method. So this is the clean image with a confidence value of 41.82% to this breed. So basically, since our main goal is to introduce the perturbations in order to maximize the loss value, but the loss value should remain in the inner limit such that the difference between the clean image and the perturbed image is not visible to the human eye. So for that case, for each pixel here in this block of code, for each pixel, we are calculating the gradient value, the direction in which we should move in order to maximize the loss value. So that leads to the, and then we convert that into an perturbed image, which forms an image of this sort. This image is then added to the clean image in order to produce a perturbed image like this. And as we can see, as we keep on keep on changing the epsilon value, the model classifies each image to a different target value. Here in our case, it each time um, classifies the image to a different breed of dog, as we can see. So as we keep changing the epsilon value, which is the parameter of perceptibility, the perturbed image keeps changing, and the target label also keeps changing. The second example which I'll be demonstrating is, so in one pixel attack method, uh, basically we define the perturbation of pixel as a 5 tuple, where the x1 and x2 here denote the coordinates of the pixel and then the RGB values to which we want to change that pixel. So then we concatenate each of these tuples. Basically, we're creating multiple copies of the clean image, and then we are adding perturbations of this form to each image, but one pixel at a time, and that leads to uh, uh, change in the target label of the image. So each time we change a different pixel, and then we keep on recording as to which change will maximize the loss. So, and then the pixel which leads to the maximum increase in the loss function, we take that into account, and that is the final adversarial example or the adversarial image. So in this case, we introduce that the coordinate at the pixel at this at 16 comma 16 coordinate should be changed to a yellow color. So this is how the perturbations are introduced. Then here we have two variants of this model, which are the targeted versus the untargeted attacks. So in the in the untargeted attack, Mm, In the untargeted attack, we have not specified the target label, so the confidence value of the correct label should keep on decreasing with each iteration, as we can see here. This is happening, and in the targeted attack, the we have specified a particular target label for the image. So the confidence value of the new target label should keep increasing with each iteration. As we can see, it has increased from 0.07 to 0.5. So this was the demonstration for the one pixel attack. So now we'll continue with the second part of the presentation.
Okay, so now we will look into how these actually exist in the first place. How it is possible that the human eye classifies them right, but the machine classifies them wrong. Now, there are varied views regarding this topic due to various observations by researchers, but often all of them fall short. Some viewpoints can be seen here: linear hypothesis, flatness of decision boundaries, etc. Here you can see that linearity hypothesis actually really well explains FGSM, but it was demonstrated that linear classifier do not actually suffer from adversarial examples, which is not in line with the linearity hypothesis. Thus, we can say that not all of them actually come to in a generalized manner. Now we will discuss the phenomena resulting in the existence of adversarial examples. First is the limit of adversarial robustness. Now the distinguishability measure of classes limits the robustness of classifiers due to which adversarial examples can exist beyond deep neural networks. Also, adversarial examples have high dimensionality, because of which they have high transferability also. Due to this, even the shallow networks, even the adversary examples of shallow networks can act as adversary example for deep neural networks. Now the boundary tuning perspective. Now the deviation angle of boundaries, that is the difference or the angle between two different decision boundaries, determines the adversary strength of a classifier. Now this strength can be changed by boundary tilting as it mainly depends on the boundaries. The main reason why adversarial examples actually do exist are because of uncertainty in the neural networks. Also, because of evolutionary styling, which is necessary for training the data. Due to this, some examples which are already set right are not used in the loss function. Due to this, those examples can actually act as classifiers or exam or as future uh, adversary examples. Many experiments led to the observation that neural networks with high classification accuracy also exhibit more robustness. They also conducted experiments that adversarial examples transfer between similar network topologies. Also, some authors have demonstrated that adversarial examples generated using DAM models with smaller interaction power can also be used for a deep neural network with ReLU activation. Due to this, we are able to fool models which are having higher order interactions. Existence of universal perturbations. Universal adversarial perturbations exploit geometric correlation between the decision boundaries induced by the classifiers. Their existence partly owes to a space containing normals to the decision boundaries, such that the normals also surround the natural images. Now let us discuss the defense against adversarial attacks. Currently, defenses against the adversarial attacks are developed along three main directions: modified input, modified networks, and network add-ons. Modified training input simply refers to modifying the input data to our needs such that adversarial attacks are not effective. First method is simply brute force. We can simply brute force all the adversarial examples in the trained data such that the model itself trains and increases its robustness for the adversarial training. Data compression is also a very good example because sometimes after compressing data, it is possible that adversarial perturbations are effectively removed. Also, due to strong compressions, it is possible that the clean image reduces its accuracy. There is also randomness and foveation are methods which can also be used while applying neural network to increase its robustness. Foveation is a technique in which a number of neural networks are applied to different regions of images. This is used basically in CN-based classifiers trained on large datasets like ImageNet and are generally robust to scale and transition variations, but not to adversarial patterns. Due to this, foveation is a reliable method. Randomizing and adding random pads also reduces the effectiveness of the in fueling the neural networks. Literature says that techniques like Gaussian data augmentation during training can slightly improve neural network robustness against adversarial attacks. Now we'll talk how the network can be modified. We can use deep contractive networks (DCN) to robust deep learning. Now these use a smoothness penalty similar to autoencoders, which improves robustness against adversary examples. This show decent robustness against LBSGS attacks, but face challenges from stronger attacks. By regularizing the gradient, the robustness can also be increased. Input gradient regularization, penalizing output variation, and along with brute force adversarial training, these also show high resilience against FGSM and JSMA attacks, but increases the training complexity significantly. Defensive distillation is another method to make this robust. It again works against FGSM and various other adversary attacks. It simply involves transferring knowledge in form of class probabilities, converting the hard labels into soft labels. Natural robustness of neural networks against adversarial attacks containing nonlinear activations, similar to nonlinear dendritic computations, which are biologically inspired, are also make the model robust towards adversarial attacks. Parseval networks can also be used as defense against adversarial attacks. These networks employ layer-wise regularization by controlling the global Lipschitz constant, mitigating small input perturbations, and the spectral norm of weight matrix controlled using the Parseval tight frames, leading them the name Parseval networks. A number of other miscellaneous approaches like bounded RLU, adaptive noise, hypernetworks, and building-based regularization can also be used as defense against adversarial attacks. Now network add-ons. Defense against universal perturbations. This frame involves appending the prenet layers named perturbation rectifying networks to target network. Due to this, the perturbated image uh, due to this, the perturbed image is rectified according to the classifier scheme predictions. Now for this, a separate detector can also be trained to identify the perturbations by analyzing input-output differences in the PRN features. The GAN-based defense. The GAN framework is used to train network resilient to FGSM-like attacks. Their approach involved training the network alongside a generator network which is responsible for generating perturbations with classifier aiming to correctly classify both clean and perturbed images. Detection only approaches. These approaches are basically used for detecting and reducing the effect of adversary perturbations. Feature squeezing. Feature squeezing is used to detect adversary perturbations by reducing color bit depth and applying spatial smoothing to the images. This approach effectively countered classical and CNW attacks by comparing predictions on the original squeezed images. Magnet. MageNet framework identifies adversarial images by learning a manifold off-screen images during training and ejects images far from manifold testing, simply removing all the perturbations. A number of other methods can also be used, for example, removing noise and applying persistent homology to detect adversarial examples. Now, we'll be looking into how actually defense is happening against FGSM on the MNIST dataset. Here, this is the code for the MNIST dataset. Now, first we fit the training data on the basis of our training cell and computed the loss. Now, for attacking, we used FGSM, IFGSM, and MIFGSM attacks on the testing data. After perturbing the images using the following, we saw at different value of epsilons, test accuracy decreased. For example, for FGSM it was 0.248, similarly for IFGSM 0.3, and so on. To defend against this, we simply added a layer of distillation. Over here, we can see All the hard labels are transformed to soft labels using softmax and by using probability of other classes, that is by transferring knowledge of other classes to the same class. After using classification in these soft labels, we saw that after number of epochs, for even for different value of epsilons, the test accuracy did not fall as much as before. As you can see, for FGSM, it is still 0.8 instead of 0.24. Similarly, for IFGSM, it is still 0.8 instead of 0.3. Now, this field actually is a real threat for adversarial attacks and makes deep learning vulnerable. Since now there is a need for investigating this field, therefore it has a great outlook for research direction. Despite the high accuracies of deep neural networks on a wide variety of computer vision tasks, they have been found vulnerable due to these substitute perturbations. Now, with deep learning at heart of the current advances in machine learning and artificial intelligence, this has resulted in numerous recent contributions that devise adversarial attacks and the defenses for deep learning. In this, we mainly focus on how attacks and defense works. Also, this literature demonstrates how current deep learning cannot really be effective in cyberspace, but also in physical world. Thank you for listening to this presentation. Have a nice day.